Hey guys, I'm just continuing straight on from the previous video. So we're now up to our third boundary condition, and if you look back at our cantilever, so at the distance L, you can see we have a final displacement of F, which we said before. So we have V of L equaling F. Now if we take what we had from our previous video, the solution we reduced down to, we got up to this point here, where we had V equals A cos alpha x plus F. So that's what we've reduced down to so far. So we're going to be using that. So we have V equals A cos alpha x plus F. So subbing in for this boundary condition, we would have F equals A cos alpha L plus F. So the F's are simply just going to cancel, and we're left with A cos alpha L equaling 0. So once again, we could have two solutions from this. We could have A equals 0, or we could have cos alpha L equaling 0. Now, A equals 0 would not be a legitimate solution because we would just be left with V equals F, which sort of is legitimate, right? Because we know that at V of L, we get F, but it doesn't give us any general function for the rest of our display shape. So A equals 0 we're definitely not going to be using because it doesn't give us a legitimate solution, whereas we can use this. And at the end of the day, we want to be finding something for alpha. Now, cos alpha L equals 0. Hopefully you remember back to maths that the cos curve looks like this. And equals 0 at pi on 2, 3 pi on 2, and it will continue on. So we need to find a general equation for this formula here. We know back from high school maths that alpha L would have to equal 2n plus 1 outside of pi on 2, where n ranges from 0, 1, 2, so on and so forth. So for example, subbing in 0, we would have pi on 2. Subbing in 1, we would have 2 plus 1, so 3 pi on 2. So that is the general formula for a cos curve, the general equation. So now we're going to get up to step number 4, where we're going